Say you want to learn about the birth of the universe. Well, you could do one thing: call the doctor, hop on a TARDIS, and travel back through the fabric of space and time to the very beginning of it all. Well, I must add, the beginning we think we know. But given that you're here watching this video, I think I can assume that you're done with that, waiting for aliens and time machines to appear in your garden. But don't lose hope already, for I have an alternative for your wobbling heart. Science! Why depend on timey-wimey machines when you have a spectacle into the universe at your own disposal? Now then, the beginning of the universe, right? Well, as you may already know, the current theory of the universe, i.e., the Big Bang, states that at the beginning, all that ever was, is, and ever will be was located at this one point. Well, loosely, that's what it says. And as it expanded, so did the space and time around us. It was literally the birth of everything. Well, moreover, since so much was squished together, the beginning was extremely hot. For more, so then, if we want to reconstruct and study the scenario that must have existed back then, we have to create a Big Bang for ourselves, don't we? But wait, what? Big Bang? Here? On Earth? Stuff a million times hotter than the sun. On Earth. I know what you must be thinking. I've gone nuts. Well, turns out physicists can actually do this. In fact, they do it quite a lot. But before that, let's review some basic concepts of physics. You see, most of the stuff around you is the way it is because of bonds. Bonds between particles, atoms, molecules, crystals, etc. And they are so because after billions of years of their births, the particles that make up any system have reached an equilibrium in a sense. They are stable, have low energy. It is almost as if they stumbled upon a state where they could rest on a cozy bed, became lazy, and now prefer to stay that way. And since they interact with their neighbors, they end up forming a colony of stable, lazy, bounded particles. At this point, you're reminded of the glass plate you once broke and your mother almost broke you. Wait, why did the plate break? Didn't we just construct a theory of how stuff is stable the way it is? Well, you see, anything that breaks, be it a plate, a chalk, a molecule, your heart, or even an atom, is because you supply energy into the system. When the plate hit the floor, the reaction force was high enough to supply energy and excite the bond, make them jump around, furious, and finally break it. The bonds making up the plate literally become a bunch of angry souls, red hot with anger, who cannot even digest looking at their partners and just want to go far away from each other to cool off. You could say, in a way, the particles were on a break. But breaking plates is one thing, and creating stuff million times hotter than the sun is another story altogether. So, how do the physicists do it? We know that atoms are made up of protons and neutrons, together called the nucleus, and electrons whizzing around them. Well, roughly that's the case. And as you can imagine, with a glass plate, the harder the smash, the more is the number of cracks, and thus smaller are the glass debris pieces. So in physics, when we want to study stuff that's inside bonds, crystal atoms, we try to supply energy to the system. Initially, we have a crystal structure. Well, we make it hotter. What happens? We break the bond, and you have isolated molecules whizzing around each other. Make it hotter, and you break the molecules into constituent atoms. Make it hotter, and the electrons break away from their bonds with the nucleus, and you get a sea of electrons and nucleus called plasma. Make it hotter, and you can do away with the electrons, and you have an isolated nucleus. Now comes the tricky bit. If you expend even more energy into the system, turns out you can actually break the nucleus as well to get isolated protons and neutrons. Before we go on any further, there's stuff we got to review about the protons as well. You see, protons and neutrons are made up of even smaller stuff called quarks. Well, essentially the big ones drawn here, with the other colorful quarks swimming around in and out of existence. There are other cool things about quarks like colors and flavors. Well, basically that they come in 6 types: up, down, charm, strange, top, bottom, etc. But I don't have time to go over all of it here. But I do urge you to check out my comics on quarks to know more about them. I'll put the link in the description below. Right, so where were we? Oh yeah, make it hotter. And to do that, well, physicists and their particle colliders, of course. Particle colliders are like these ultimate toys of physicists where they make subatomic particles like protons go around in loops and tracks nearly at the speed of light. Making stuff go around almost at the speed of light makes the smash between the protons so great that they literally break into stuff even smaller. Well, note that we're talking of energy so high that it excites the protons and neutrons at temperatures a million times hotter than the sun, which literally melts them and lets the quark loose. So basically, we have a cauldron of quark soup. Who ordered that? Well, here's a close up of all those extremely hot quarks swimming around. This is similar to a universe a millionth of a second after the Big Bang. Soon enough, though, they start cooling down and start to come close to each other and form bonds. It is believed that at the beginning of the universe, similar conditions existed where hot quarks ultimately cooled and became lazy and thus formed bonds with one another, or shall I say, thus formed literally everything that we know of. To end, I will tell you a love story. Oh, don't run away already. This is a tale of the quarks. Charming as they may be, they experience love just the way we do. They interact strongly. As I take you through this saga, I want you to know genuine love comes in all flavors. Be accepting. Find what you seek, not always what you expect. So here we have Tal and Shlok. They are these charming too, always by each other's side, bounded by each other's love. The interaction they felt was strong, quite like a super glue, you could say. And if you were to try to pull them apart, their interaction between them would further increase, leaving your attempts futile. Imagining a world away from the other was simply a null option from them. Shlok must have Tal to complete the symphony of life. Their admirers called them the Jepsi particle. Shlok, a charm quark, and Tal, a charm anti-quark. And after their union, they became a part of the meson family called the Jepsi. Their love brought with itself a transparent, colorless, and honest relationship. Meant to be, weren't they? But fate had other plans. While strongly enjoying the initial excitement of the relationship, the Jepsi suffered from the cruel heat wave, distrust that hit their particle world. You know, as they say, nothing is ever strong enough. So while there was a bond so strong that breaking their confined form would be unimaginable for ordinary mortals, a heat wave of external gossip, suspicions, and doubts, i.e., heat of this high energy mistrust, literally melted their relationship, their bond. And in a moment, they went from being confined to deconfined selves. And so while they did love each other immensely, the music between them was lost. And once lost, Tal could never find Shlok. The bitterness of that heat wave drifted them apart, far apart, broken bonds. This was a sight physics could not withstand. You cannot have an isolated quark. They can't be sad. Colors don't belong as isolated selves. They must combine to restore the colorless transparency of life. Thus, while this was happening, physics was preparing for another one of its tricks. Tal traveled through space and time heartbroken, alone, and then one fine moment her path intersected with that of Meraki and Mitsuha. Like Tal's former confined self, these belong to the meson family as well. Meraki, a bottom quark, and Mitsuha, a bottom anti-quark. Together, their couple was nicknamed the Upsilon. But none of this mattered now because from the moment Meraki laid eyes on Tal, he was already Tal's. Meraki wondered what could be the cause of sorrow on the face of the most beautiful and charming quark he had ever seen. And once Tal opened the eyes, a vision so serene, Meraki knew at once that this was love, and in a soft, quiet voice gave an introduction. Unparalleled, unmatched surge of emotions filled Meraki. I have to be the one beside Tal, and in a strong bond, the two of us confined to become one. So while Meraki did like Mitsuha very much, deep down it was known that Meraki is incomplete, in search of something, and today it seems as if it was found. Meraki asked of Mitsuha to let go, for they couldn't stay in a false relationship. Mitsuha, though angry, realized that Meraki was not at fault. Love is what it is. As for Tal, initially apprehensive of this proposal, the tone of honest faith and love in Meraki's voice gave in. Meraki did not place dreams and wishes on his steps, but rather promised the company besides and asked for the same in return. While Mitsuha was sad for now, little did Mitsuha know that in this world of Quark Gluon plasmas, there floated many other quarks out there, and in them, if one is open to adventures, resided Mitsuha's confined. Well, that's the end. This is what happens at CERN. You smash two morbidly small particles at high energy to create situations much like the beginning of the universe. But then what? Well, take snapshots, click pictures, make notes, read data, and present results. This is much of the job of Alice, the Alice detector. As it turns out, one interesting bit we want to study is that of strongly interacting quark. Reason being, our bet is that knowing about how they interact will open up new doors in our search of the fundamental. Turns out, the collision of the sort mentioned above leads production to these charming Jepsi particles. But now what? Well, once you perform the collision, you want to test whether it was a collision massive enough to replicate the universe, right? Well, if our collisions are to replicate the Big Bang, they must go through a soupy phase as well. That's where the Jepsi enter. You see, a collision, let's say, creates 10 Jepsis in a seeming hot, dense, soupy environment. Then almost immediately after their birth, these particles would literally melt in a soup and float around as deconfined free particles. As time passes, heat is radiated off, things cool down, and free quarks again start forming couples. But note, this time the charm quark is not necessarily bonded to a C bar, but instead it might bond with, let's say, a B bar quark, as depicted in the drama above. Thus, even though you calculated a flux of 10 Jepsi, your data would show a lesser flux, i.e. a suppression, thus confirming that your collision did sort of replicate our nascent universe conditions, i.e. the soupy phase. This is what the Alice experiment at CERN does. It tries to reconstruct the early universe using pictures taken of the quark gluon plasmas and then takes the data of the system for further study. I think I'm going to end with that for today. Thanks for watching the video, and if you want more intel on the drama that goes on in the particle world, make sure to visit the website link in the description below, Fatal Physics. Make sure to like, subscribe for more. Thank you. Keep sciencing.